this input and output together, these are the two plots that I'm looking for. Okay? In one figure, you just show me these two plots. So this is your output, which is, I call it VR. So this is your VR, and this is your input voltage IT, and this is your output voltage VRT. So these are the inputs. This is the input and output waveform I'm looking for in one figure. Okay, so you just need to show this. That's all. It's very easy, guys. The due date. When is the due date? Thursday. Tuesday. Put the due date Tuesday. November 4th. November 4th is Tuesday.
Originally you said we do on Thursday. Yeah, I think he said Thursday.
Okay, I'll change it to Thursday. It doesn't hurt me at all. But the thing is, you will have to do it. I can change it to Thursday. I usually keep 1 week for this problem, but it's going to take a couple of minutes for you guys. All right. So let's move on to our next module. Which is field effect transistors. So this is basically chapter 5. Chapter 5 of our textbook. Chapter 5 of our textbook, and I plan on finishing with chapter 2 in one lecture. And one lecture for BJT, which is chapter 6, and then we will be spending the rest of the semester, the rest of the lecture on chapter 7, which is amplifier, how to build the amplifier using MOSFET and BJT. So this MOSFET, metal oxide semiconductor field effect transistor. This MOSFET is the transistor. This is the semiconductor device that you actually see in high speed chips these days, NVIDIA chips. I'm not advertising for NVIDIA, but high speed processors that you see these days. These are built using MOSFET. Trillions of transistors. Today I will be going over theory. I have one example. Make sure you understand the theory, operating principle, how it works. Okay, if you understand, then it's very easy for you to conduct lab. I plan on having one lab based on this MOSFET. We have ordered parts. Parts should arrive next week. So once I have the parts, then I will be listing the part number, the specific part number. Then you will conduct one laboratory based on which is going to be based on MOSFET, metal oxide semiconductor field effect transistor. So make sure you understand theory, operating principle, construction of this MOSFET properly. That way it will be easier for you to conduct laboratory. Lab is not that hard. introduction. So these metal oxide semiconductor field effect transistors, these are three-terminal devices, three-terminal semiconductor devices. Terminal 1, terminal 2, terminal 3. They look like this. So you have 3 legs, MOSFET that you will be working with. They look like this. So you have something to hold and you have 3 legs. Yes.
What does MOSFET stand for?
Yeah, I'll talk about it. I'll talk. This MOSFET, this transistor, you can think of this transistor for a moment. So I have the detailed TWS. This transistor, it's a 3-terminal device for the moment. You just think of this as a 3-terminal device that can be used from signal amplification. Signal amplification, it's for analog function. Analog function. Signal amplification to digital logic, processing, addition, subtraction, multiplication, multiplier, adder, subtractor. So you can use digital, you can use these semiconductor devices to implement digital logic circuit and memory as well, the storage device. This device can be used as a control source. So the one that we'll see today is, I'm not sure if you have heard of it, 240. Voltage controlled current source. Voltage controlled current source. So you actually control the amount of current to flow using voltage. That voltage is going to be, the concept is like this, guys. So you came through this door, right? There is a gate, okay? So I control the amount of space right here. So I am the controller, voltage, I'm controlling the voltage. Using this voltage, I control, how fast you guys will be flowing. So you guys have the current, okay, how fast you'll be flowing right here. If I close the gate, less people will be able to come through this gate. So we have a terminal called gate in this device. So we have 3 terminal devices that can be used as control source. So using voltage, we can control current. And these can be used as a switching device as well for logic inverter. Okay, this device can be used as a switching device. Now, 2 major types of 3-terminal semiconductor devices. One is called MOSFET, metal oxide semiconductor field effect transistor. That is the elaboration for MOSFET. Metal oxide semiconductor field effect transistor. And another 3-terminal device is called BJT, bipolar junction transistor. So this is going to be covered in chapter 6. MOSFET is very important these days because it requires less power. MOSFET requires less power, is mostly is widely used in building electronic ICs, integrated circuit. IC stands for integrated circuits. So the op-amp IC that you see, op-amp IC, which is LM6484, op-amp IC for example. It requires less power and very small, very, very tiny. And you would say, I will go through one example on silicon chip. We use silicon materials to build this MOSFET. And MOSFET can be used to implement both digital and analog functions. Analog functions, for example, amplifiers, filters. So these are analog functions. This MOSFET can be used to implement analog functions as well as digital functions. For example, in logic inverter, memory, adder, subtractor. So therefore, both analog and digital functions can be implemented on the same IC. That's why these MOSFETs are used for mixed signal design. Mixed signal means on the same IC, you can have both analog and digital functions. Field effect transistor classification. Field effect transistors mainly classified in two different categories. One is called JFET, junction field effect transistor. The other one is other category is MOSFET, metal oxide. I'm going to go through why it is called metal oxide in a moment. And then this MOSFET operates in two different modes. One is called enhancement mode, and the other one is called depletion mode. Enhancement mode is divided into two categories: N-channel enhancement mode MOSFET, P-channel enhancement mode MOSFET. And this chapter talks about depletion mode, enhancement mode, N-channel, P-channel, N-channel, P-channel, and also this chapter talks about JFET as well. But the reason I said that I will be able to finish this chapter today is because I will be focusing on only MOSFET, enhancement mode, P-channel. Yeah, so this is the transistor that I will be focusing on. N-channel. So MOSFET, enhancement mode, N-channel, and this is the symbol. This is the transistor that you will be using in the lab, and this is the transistor that I will be focusing on to explain its construction, theory, its characteristics. Why I don't go through the other one? P-channel is just the opposite of N-channel. Okay? And the mode, so again you have N-channel, P-channel for depletion mode as well. The mode is completely opposite as well. So that's why I will be covering the theory that you need to conduct the laboratory only. So the basic, if you understand the basic of one transistor very well, the basics of other transistor will disappear. The symbol for MOSFET is given right here. So it's my symbol. Author did not give this circle. I put the circle just to make sure that previously actually some transistors you see those are circular shaped. Okay, there are three legs, but those are circular shaped. So that's why we put circle there, and then it has three legs. One leg is called gate, the other terminal is called drain. So this is gate, this is drain, this is source. So this is gate, this is drain, this is source. So you control the gate voltage, you actually apply gate voltage to control the current flowing from drain to source. Okay? So current is actually flowing from drain to source. Electrons flows from source to drain. Electrons flows from source to drain. Current flows from drain to source. Okay? Current flows from drain to source, and electron flows from source to drain. but I'm not a PSC.
Is it a one-way circuit like a diode or no? Like current only for one way in this? Or?
Yes, yes. And the amount of current you control, the amount of current you control is through this gate voltage. Okay? So that's why it's called voltage control current source. So you can actually control the amount of current that flows from drain to source through using gate voltage. And you will know how, because I will go through the construction mechanism on this enhancement mode N-channel MOSFET. And in short, enhancement mode N-channel MOSFET, people call it NMOS. Even in the data sheet, you will see that. So NMOS. NMOS means it's N-channel MOSFET. Now I will talk a little bit about the construction, device structure, the structure of this N-channel MOSFET. In chapter 3 or module 3, we talked about diode construction. Diode is constructed using N-type materials and P-type materials, right? We went through this. Diode is constructed using N-type materials and P-type materials. So N-type means that the material is doped with phosphorus, and P-type means material is doped with boron. Okay? So we have N-type. This MOSFET is actually built on a base. So this is base. In technical term, it is called substrate. So this is basically base. It has a base. Base is constructed with P-type materials. So you have P-type materials. You have P-type materials that are used to construct the base. So this is the base, and then two heavily doped N-type regions. So these are two regions here. These regions are heavily doped with N-type materials. So one is called source, the other one is called drain. Okay. Now, this source region, on top of source region, there is a metal right here. Metal right here, and there is an electrode that actually there is a terminal that comes out of it, and this is the source terminal, and then there is a metal placed on top of this N-type material as well, and there is electrode coming out, and this is your drain terminal. This is your source terminal. Now the gate, you see this part, you put a metal right on top of it, and there is an electrode coming out, and this is your gate. Okay. Now what you do, the base you have P-type materials, and then you have a metal. So in between you insert some dielectric materials. It's called silicon dioxide. Okay. In between, you put some dielectric materials. Just like capacitor, you learned in 214. So capacitor has two plates. Capacitor has two plates. Capacitor has two plates, and in between you have dielectric materials, and these dielectric materials are used to store. These materials can be used to store energy. So you have some dielectric materials here. Dielectric material. So if you put some dielectric material, then there is these two plates can be used to store energy, and capacitor is an energy storage device, right? Capacitor is an energy storage device, because if you have charge in both plates, so there is a voltage across this capacitor. So capacitor is an energy storage element. Exactly the same principle has been used right here. So you have a metal right here, it's a plate, and you have a base which is constructed with p-type material. In between you have dielectric material, silicon dioxide. In between there is an oxide layer. It's called silicon dioxide. Now, because of this silicon dioxide, because of these dielectric materials, what you have, I'm going to use this color. You have electric field generated. Electric field is generated because of these two plates. You can just think of these two plates, and in between you have silicon dioxide material, and because of this, an electric field is generated, and that is the reason it is called field effect. You know, the reason it is called field effect. That is the reason it is called field effect. So there is an dielectric material, and because of that, electric field is created, and that is the reason it's called field effect. Okay, field effect. And metal, because you have this metal, and because of this metal, because the oxide, silicon dioxide layer is in between metal and the substrate, and that's why we have metal, oxide, semiconductor. And that's how this naming convention stems from or came from. So electrode is formed with metal deposited on oxide layer, and then metal contacts are made on source, drain, substrate, and this body, this substrate body, it has no impact on the operation of this device. So that's why, even though there is another terminal at the base, okay, B terminal, this B terminal is not shown in any of the MOSFET devices because it has no effect on the operation of this MOSFET. So that's why we don't show the base B terminal, but there is a B terminal as well. B terminal has no effect on the operation of this MOSFET. So we just show these three terminals: gate, source, drain. And once you apply certain gate voltage, so let's say you connect it to the battery or voltage source. Once you apply some gate voltage, okay, so voltage applied to the gate controls the flow of current from drain to source through channel region. So channel region, I'm just going to talk a little bit about channel region in a moment. So once you apply this gate voltage, then the current flow from source to drain, this current flow, identified with ID, this current flow is going to be controlled through the voltage applied at the gate terminal. So that's why this is called voltage, you want to just write it down, voltage controlled current source. Voltage controlled current source, voltage controlled current source. In short, we will call it like that. Okay. So now, this device, you can think of this as a voltage controlled current source, and this device is used for implementing both analog functions. Analog functions, for example, amplifier, to amplify the signal, and this device can be used to implement digital IC, digital chip, storage device, memory, for example, processors. Now, let's see why it is called N-channel. The reason it is called N-channel is the following. So I'll start from this figure here. figure 5.1 of the textbook. Okay, guys. So N channel, N-type materials. What does that mean? You have lot of electrons. N-type materials, you have lot of electrons. So we went through this in chapter 3. So you have lot of electrons here. E minus, E minus, E minus, lot of electrons. Here we have E minus, E minus. Now, let's say I connect this source to the ground and drain to the ground. Please pay attention. See how this device works. I connected source and drain to ground. Now I'm going to apply some voltage right here. So voltage with respect to this source. So we call this VGS. So VGS is basically VG minus VS. Voltage of gate with respect to ground minus voltage of source with respect to ground. And because source is ground, that's why you can just call this VGS as such. Okay? So now we are applying some positive voltage at the gate. With respect to source, we are applying some positive voltage. Now, P-type material, substrate is constructed with P-type materials, right? Substrate, the base is constructed with P-type materials. P-type materials means you have a lot of holes here. If you remember from chapter 3, you have a lot of holes. P-type materials, you have a lot of holes. Okay. And we have electrons right here. Once you apply the gate voltage, guys, see how it works. Once you apply gate voltage, what it does, if you have North Pole, if you have two magnets, both of them are North Pole, they repel each other, right? And South Pole and North Pole, they attract each other, right? So that's what we learned from, grade 9 or so. So now, this positive pole, the positive charge, will actually repel each other. So what you will see, these guys will come down. These guys will come down. So these positive poles, positive charge will come down. So they will come down, and instead, because they will come down, now these electrons will be right here. Some electrons will be here. These positive poles will be out. Some electrons will be attracted by this positive charge. So these electrons will be attracted. So therefore, you will see a channel. You will see a channel between the source region and source and drain. You will see a channel of electrons. And that's why we call it N channel. So external voltage, the gate voltage is used to create channel, to enhance electrons. That's why it is called enhancement mode, which means that external voltage is actually enhancing these electrons, enhancement mode, and this channel is created with N-type materials now. So this channel is created with electrons. Okay? So this channel is created, so electron will flow this way. Therefore, if you apply some voltage right here, current will flow from drain to source. Current will flow from drain to source. Or in other words, you can just say like this. So this is the current direction. Current will flow from drain to source, and because there is a channel here, we have N-type materials, electrons flowing in this direction. And this is exactly shown in this figure. So you see, we have some positively charged P-type materials, positively charged was right here. So this positive charge would be post way, would be post way. So there should be a region, there will be some space, because these positively charged holes will be post way, and there you will see a region created like this, and this region is called depletion region, because you are applying some voltage. Because of that, positively charged holes will be post way, and there will be some region created around it, and it is called depletion region. And some electrons will be attracted to create this channel. So it is called induced n-type channel. So electrons will flow in this direction. Electrons will flow in this direction, and your current, because electron is flowing in this direction, current will flow in this direction. And this current is called IT. This current is called IT, drain current. This drain current would be actually controlled by this gate voltage. If this gate voltage is more, channel width is going to be more. Channel width is going to be more, and more current will flow. If the gate voltage is less, channel width is going to be just like the door, that the example that I used, door. If you have more space, more people will be able to come in. If you have less space, less people will be able to come in. So you are actually controlling the amount of current flowing from drain to source using the gate voltage. Now, there should be a minimum voltage. There should be a minimum gate voltage to create this N channel. And that minimum voltage is called the threshold voltage VT. This minimum voltage is called the threshold voltage VT. Sometimes we will be using VTN. Sometimes don't be surprised if you see this symbol VTN. Sometimes we'll use this TN to make sure that we are working with NMOS. Okay? The minimum gate voltage that you need to create the N channel of an NMOS is called threshold voltage, which is for NMOS it is denoted with VTN, and in general it is VT. Now that's the threshold voltage. The amount of charge in this channel is controlled using the effective voltage. It's called override voltage. It's called override or effective voltage, which actually the voltage you apply to the gate with respect to the source, voltage you apply to the gate with respect to source minus this threshold voltage. So voltage you apply to the gate minus this threshold voltage is called the effective voltage that actually controls the amount of charge that you have in the channel. Very important. And we will be using that. In your laboratory, you will determine what is the effective voltage and what is the mainly effective voltage we are interested in. The gate voltage you will apply externally. I will try to simulate, this is the first time I'm studying this chapter as well. I will simulate this MOSFET using PSpice, and once I'm comfortable, then I will probably write a handout, or you can use the author's textbook. We have a laboratory book associated with this textbook. I can use author's textbook, or I will see if I can create a handout. If not, you will be using author's textbook lab. So we will be, we are interested in override voltage. Now, so far we did not apply any voltage at the drain. Okay? At the drain terminal, we did not apply any voltage. We did not apply any voltage at the drain terminal. We just applied voltage at the gate terminal, voltage with respect to source. Okay? We applied there. That's why we see that this channel is uniform. This channel is uniform. Now, we apply, keyword here is small. Keyword here is small VDS. VDS cannot be large. If VDS is large, there is another, there is a completely different mode. Okay? Completely different mode. But keyword here is that you apply small VDS. What is VDS? VDS is the voltage you apply at the drain terminal okay, so I'm just going to going to use the simple test. So you have the gate, and then gate, and then base. Gate and base, there is an oxide layer, right? That's why there is a gap. In the symbol there is a gap. So this is your gate, and then you have here drain terminal, and you have the source terminal. So you apply voltage between gate and source. Gate and source. So your gate voltage with respect to source. Now you apply voltage with respect to. So this is your VDS. If the source is connected to ground, if source is connected to ground, then you can simply say VGS equals VG, and VDS is simply VD. Now source is connected to ground. So we are applying voltage at the drain terminal with respect to source, but this is, the keyword here is small. And how small it is, you will be clear in a moment. Okay? Keyword here is small. We are applying small VDS. So if we apply small VDS, if we apply small VDS and gate voltage, the gate voltage with respect to source has to be more than the threshold voltage. If we do that, then device acts as a resistance. So please write it down. So what I'm going to do, I apply here small voltage and this gate voltage. This device, the current flowing through this drain is going to be ID. Current flowing through this drain is ID. This device, see how simple it is. This entire device, you can just think of this ID equals VDS over R. Simply D this you will not find in the book. This is your source, and then you have this resistance, and this resistance is going to be as a function of VGS. This resistance is going to be a function of VGS. So now this resistance can vary using VGS. Therefore, if resistance varies, current flowing through from drain to source will vary as well. So this ID. So current flowing through this resistance will vary. You understood, guys? So for small VDS, you can just think of this device as a resistance. How is it? Is through some experimentation, the channel conductance, this channel conductance. What is conductance? Conductance is opposite of resistance, right? R equals 1 over G. Remember? G is the conductance, G is conductance, and R is resistance. If resistance unit is ohm, what is the unit of conductance, guys? Can you say one over n? Who said it? S? Yeah. S is for sinus. So people call it mho as well. Mho is symbol like this. It's called mho. Okay? But the technical term is sinus. The scientist sinus. G. My handwriting is too terrible. Okay, G unit is Simon. Okay, so G is called the conductance, which is 1 over resistance, is called Simon. And this conductance, channel conductance is proportional to VGS minus VT, which this proportionality constant is determined using this expression, which is mu n COX W over L, and this is called K sub n. K sub n, I'm not going to write it down, I wrote it down here. K sub n is called MOSFET transconductance parameter. K sub n is called MOSFET transconductance parameter, and mu n is the mobility of electrons at the channel surface. So mu n is the mobility of electrons at the channel surface, and COX is the oxide capacitance. COX is the oxide capacitance, and oxide capacitance is also depends on the permittivity of the material, oxide material, and the thickness of the oxide layer. So thickness of the oxide layer is this much. It's very, very tiny. We have all the physical dimension in the example. That I'll go through in a moment. So you have very tiny thickness, and this is the channel length. Channel length is shown right here. This is channel length, and channel width. Channel width is basically, this is the channel width. This is channel width, and this is channel length. Channel length, and this is the width. We now have all the parameters. So this is your MOSFET transconductance parameter, which is mu n C oxide capacitance, W over L, and VGS minus VT. Now, this Kn VGS minus VT is basically your G conductance. This is your conductance, which is conductance G, which is 1 over R. And this R is basically 1 over, this quantity is the resistance. That you control using this resistance, you control using this VGS. The voltage we applied at the gate terminal, you control this resistance using VGS. Now this conductance between drain and source is denoted with GDS. GDS is the conductance. The conductance, where RDS is basically 1 over GDS. The conductance between drain and source, in other words, resistance between drain and source, is given as such: Kn VGS minus VT. So if I go back to my equivalent circuit here, this resistance is basically R as a function of VGS is basically 1 over GDS, which is basically 1 over, anybody remember? Kn transconductance parameter times VGS minus VT. Yeah. So this is basically the resistance that you see between drain and source, and this expression is basically the conductance between drain and source. Now so I I use my formula, I use programming language to actually plot it. I use LaTeX, and here what I did, I chose Kn to be 0.5, Kn to be 0.5, which is trans parameter, and you see that this IB versus VDS, it's linear, which acts as a resistance. Resistance is a linear device, right? Resistance, it's a linear device. Here, resistance is controlled using VGS. When VGS equals 2 volt, you see that the current and voltage VDS relationship as such. If VGS is more, you get more current for less voltage. As you see, VGS equals 4 volt, you have more current for less voltage. Okay? So that's, as you increase VGS, you are basically increasing, as you increase VGS, you are increasing conductance. If you increase conductance, resistance goes down or up? Resistance increases or decreases? If you increase conductance, resistance decreases. If resistance goes down, then current goes up, right? And that's what it is. So I use, for plotting purpose, I use Kn equals 0.5, and you know the VGS, and you know VDS, so therefore you should be able to draw these graphs. But again, this mode is valid when the when the VDS is very small. VDS is very small. Now we are going to gradually increase the VDS. But this time we are going to keep the VGS constant. If the gate voltage is constant, and you know that because of this capacitor, the capacitor is forming, no current will flow here because this is DC. You are applying DC voltage, and you can think of this as a capacitor plate. Okay. So capacitor, if you have a capacitor for DC signal, capacitor, you treat capacitor as an open circuit or closed short circuit. Why IT here is 0? Okay, you have a capacitor right here. You apply battery voltage. Vs equals 5 volt DC. My question to you, what will be the current? And you have a capacitor. Yes.
Is it injected? Zero.
0. Current is going to be 0. So that's why for DC signal, for DC circuit, you can think of capacitor as an open circuit. You can think of this capacitor as an open circuit. No current will flow. Okay? But if you replace it with inductor, which I will not confuse you, then it is going to be infinity, because for DC signal, it is going to be 0. The resistance is going to be 0, therefore current is going to be infinity. So for capacitor, this is going to be 0. So same concept is happening right here. So you have if VGS is constant, so therefore no current will flow, gate current is going to be 0. Now what you will see, as you increase VDS, so channel length depends on the voltage between gate and points along the transfer channel. So this channel length, so if you take the voltage between this gate and this one, gate and source, it is going to be your override voltage plus the threshold voltage, because you need some charges, so which will be controlled by override voltage, which is the difference between gate voltage and threshold voltage. So you apply gate voltage, which is threshold voltage plus override voltage. So this voltage is going to be, you apply voltmeter, this voltage is going to be VGS, which is threshold voltage plus you can have some extra voltage, override voltage. So that's why you see this channel is wider here. Now as you move this voltmeter negative terminal through this channel, you go across the source, you will see that VGD, voltage between gate and drain, is going to be VGS minus VDS. Now if you increase VDS, what is this voltage, guys? If you increase this, it is going to go up or down. VGS is constant. VGS is constant. If you increase VDS, what will be VGD? It will decrease, right?
Yeah.
VGD is going to decrease. So which means that the voltage between gate and drain here is going to be decreased. It is going to go down. Now this channel, don't you guys remember, do you remember I said that this channel width depends on the voltage, amount of voltage we apply at the gate. So more voltage we apply, channel width is going to be more. And less voltage we have, channel width is going to be less. Because you are increasing VDS, we are going through another mode of this transistor. Because you are increasing VDS, this gate voltage is going to be less, therefore channel width is going to be less. Channel width is going to be less. Here you have more electrons, here you have less electrons. So this is actually explained using this graph. So this is your VGS is going to be VT plus override voltage. Now, so this is your source, this is drain, this 0 to L is the channel length. Now you see that the voltage that you have here, is 0 at the source. Now this voltage is going to keep increasing. As you increase VDS goes up all the way here, and VGD is basically VGS minus VDS. So now, at some point, you will see this channel length. If you keep increasing VGS, channel length, the channel is going to look like this. Channel is going to look like this, and it's going to come right here, which means that time, even if you increase VDS, current will not go, current will not increase, current will be constant. So that is the saturation region, and I will show saturation region in a moment. So you keep increasing VDS, and therefore channel on the other end is going to be narrower. That's why I say that. As VDS is increased, channel acquires tapered shape, narrower, near to the drain. And that time, your current is going to be constant regardless of your VDS. Even if you increase VDS, your current is going to be constant. So VDS, you can go up to this point, which is override. VDS equals V override voltage. So up to override voltage, your current is going to increase, just like a linear relationship because of the resistance. And after that VDS, if you increase VDS becomes large. If you increase VDS, that time here, if you increase VDS, VGD is going to be less. So therefore, doesn't matter how much your VDS, regardless of VDS, current is going to be constant. And this mode is called saturation. So here your VDS, and this is your ID. You keep increasing VDS, so up to certain point when VDS equals VOV. Up to certain point, you will see that current is increasing linearly as such, and after that, even if you increase VDS, current is going to be constant, and this region is called saturation region. And now you have different curves here because you have different VGS. So different VGS will give you different curve, but up to this point, it's linear region. People, technical term is called triode region or active region. So up to certain VDS, your voltage current relationship is going to be linear, but after certain VDS, your voltage current relationship will not be linear, current will be saturated. Current will be constant. So here, as you can see, current is constant. Current is constant. After VDS greater than your overhead voltage, you can just write it down, VDS greater than or equals V overhead, I wrote it down. So VDS greater than or equals overhead voltage, the transistor MOSFET is going to operate in saturation region. If VDS less than or equals overhead voltage, then your transistor is going to act like a resistive device, active region. Okay? And we are going to use this formula in saturation region. In saturation mode, ID is going to be function of just the overhead voltage. So here it does not depend on VDS. Not dependent on VDS. Okay? So that is the saturation mode voltage current relationship. Here we have generic relationship, and when VDS is small, this is the voltage current relationship, which is purely resistive. Okay? Now if you keep increasing VDS, then this is the relationship, and at saturation, this is the voltage current relationship. Please include this example in the scribing. I will not go through this example. This example. Scribe. Example 5.1. I will start solving example 5.2. But before I do that, as you see here, P channel MOSFET. So construction is this substrate is N-type, and your source and drain, those are P-type. Everything is just opposite. Okay? But in the exam, okay, in the exam as well as in the laboratory, I am not going to give any problem on P channel MOSFET. Okay? So you just focus on N channel MOSFET. Just one type of MOSFET. So you understand one type of MOSFET very well, then you should be good with this.
So to focus on N channel, we still have to include P channel in our scribing?
No, because I'm not going through this P channel. Okay? So I'm not going through this P channel. This is just for your information. Because I'm not covering P channel, you do not need to include P channel in the scribe. So P channel, any circuit that deals with P channel, you may want to own it. Try to understand N channel, N mode, N channel MOSFET very well. And only one type of transistor I'm covering. So now let's go through the voltage current relationship in detail. And here we summarized actually NMOS. NMOS, I wrote NMOS right here. NMOS transistor operates in three possible regions: cutoff region, triode region, saturation region. Cutoff region when VGS is less than your VT. Okay? When VGS is less than VT. So as you can see here, cutoff region, VGS is less than VTN. the reason I included VTN, author has included VTN, is because we are working with NMOS only. So in cutoff region, no current will flow, ID is going to be 0. And triode region and saturation region, we have different formulas. So you have triode region, ID, VDS, we have this formula, and for saturation, voltage current relationship is given right here. Okay? And in summary, you have voltage current relationship is shown right here. This is your VDS, this is your ID. As you can see, this cutoff point between triode region and saturation region is given right here. So up to this point, transistor operates like a linear device, but after that it is saturation, non-linear device. Okay? And saturation mode is used for amplifier design, and triode cutoff and triode modes are used when NMOS is used as switch. Okay? So very important. So cutoff region and triode regions are useful when NMOS is used as switches. NMOS are used as switches, and saturation region is used when NMOS is used as amplifier. So now let's move on to ID and VGS characteristics. Previously we saw ID and VDS, but instead of VDS, voltage between drain and source, now we have ID and VGS characteristics. ID and VGS characteristics is as follows. Okay, if VGS is less than the threshold voltage, no current will flow. So that's why you see this current. Okay, but after you pass VGS more than the threshold voltage, it follows this formula that we went through. This is in saturation. So NMOS operating in saturation gives drain current ID determined by VGS regardless of VDS. So after that you see that because of this square term, current is increasing drastically. So that's why you are actually controlling the current using VGS, and that's why people call it this device voltage control current source, VCCS. And large signal equivalent circuit, we went through this in chapter 1. So this is the VGS, and you are actually controlling the current using the voltage between gate and source, and this is your current source. This is your current source, and this current source is basically function of this override voltage. So this is the large signal model that we went through, very similar to the one that we went through in chapter 1. A large signal model of our NMOS transistor. Now let's go through example 5.2. So this is the example that I wanted to go through. So consider an NMOS transistor fabricated in a 0.18 micrometer, very small process, with the channel length equals 0.18 micrometer and channel width is width of the oxide layer is 2 micrometer. The process technology is specified with oxide capacitance 8.6. What is lowercase m? So we have farad. F is for farad, right? Right? Unit of capacitance is farad. Then we'll go by millifarad, right? After that micro, then nano, then picofarad, and then it's called vector. This F is called So milli is 10 to the negative 3, right? Micro is 10 to the negative 6. Then nano 10 to the negative 9. Then pico 10 to the negative 12. Of course, now you can guess what is femto. 10 to the negative 15. So 8.6 femtofarad over micrometer square, and then you have mobility of electrons is 450 centimeters square per volt second. So this is volt second. And then you have threshold voltage for NMOS is given 0.5 volt. Oh, it's 10:15 already. I will stop right here. I will go through this example in our next class, and then we'll move on to chapter 6 and talk a little bit about that. Thank you, guys. So your next class is going to be based on